Life on Earth began long ago. But how did it begin? And why here? Some believe it arrived on a meteorite. Others claim it began in a warm pond on early Earth. In 1953, one scientist shook the world when he proposed an answer: primordial soup. Was his theory correct? Now, researchers from around the world are racing to understand how life may have begun by creating it themselves. Each hopes to be the first to find the origin of life. Three teams of scientists from around the world are attempting a revolutionary first, producing life from scratch in their labs. Dr. Steen Rasmussen is the team leader in Denmark.
I think so. How are things going?
It's very good.
We mix organic and inorganic components, a little bit like the alchemist in the old days trying to make gold. We try to make the materials self-organize in such a way that it's able to become alive.
In Hawaii, biochemist David Diemer believes the key to life is to find out if DNA can assemble on its own outside of a cell.
And if we're really lucky, we will see some synthetic reactions go on, where small molecules join up to become larger molecules. And that would be the most exciting result of all.
And at Harvard, Dr. Jack Sostak's team is trying to install a working genetic code into a primitive cell.
We know how to make these go through multiple cycles of growth and division, so really the big step is combining that with some genetic material that's also replicating at the same time.
Theirs is a race to unlock the key to our world. But to figure out how life begins, scientists first need to find evidence of when it began. Geologist Minnick Rosing has come to Greenland to find clues to life's beginnings. He searches the ancient rocks beneath the vast ice sheet. Preserved for over 3 billion years, these rocks are among the oldest in the world. Archives of early Earth. They're exposed for just a few weeks during the summer, when snow and ice temporarily retreat. So Rosing has a short time to collect samples before ice reclaims the land. He begins his search at a remote place called Isua. He's on the lookout for unique rocks called pillow lavas. These rounded rocks formed when magma erupted and cooled on the ancient ocean floor over 3 billion years ago.
When you walk out of the helicopter, and you can see these pillow-shaped objects. And when we look at these sediments that settled on top of the pillow lavas, they are also similar to sediments you find in the oceans today. So that gives us an idea of where we were at that time on the planet. We are out in the oceans.
Earth's early seabed was pockmarked by spewing hot magma, and it's still happening today. When that 1100 degrees Celsius molten rock hits the cold ocean water, it cools rapidly, creating a rounded, rocky shell, a pillow shape where sediments eventually collect. These ancient sedimentary remains are just what Dr. Rosing and his team are after. They could contain evidence of life's origins.
So what is it exactly we're looking for now?
The origin of life.
Right.
And so that outcrop down there is the outcrop that has the evidence for the earliest life on this planet.
Wow.
The team will secure samples not only from the surface, but also from more than 100 meters below.
Where would the drill go down if you start right here?
We can have it so that your casing would be started here.
Yeah, so the drill would probably right there, or someplace.
A core drill will extract 1 ton of rock samples using a 115 horsepower diesel engine. an engine large enough to run a bulldozer. Once that engine is secured on top of the outcrop, it spins a hollow rod holding a drill bit encrusted with razor-sharp diamonds. Workers force water between an outer casing and the rod to cool the friction and flush out the shavings. After several days, they fill dozens of wooden boxes with samples of some of the world's oldest rocks.
We are done. Thanks a lot. This is going to make a lot of people happy.
They ship the precious cargo 3,500 kilometers east to Denmark's Natural History Museum in Copenhagen for analysis. Among the samples, Dr. Rosing selects one rock formed from silty black layers of clay on the ancient seabed. To find its exact age, he crushes a piece, extracting tiny minerals called zircons. No larger than grains of sugar, zircons are like little time capsules.
How's it going?
It's going good. Yeah.
When they form, each zircon captures a bit of uranium. As time passes, uranium atoms decay and convert into lead at a known rate. So by determining how much lead is present relative to uranium, the team can estimate the sample's age.
So now we are more or less ready to zap the thing with the laser.
A laser burns a tiny hole into the zircon, 1/3 the size of a human hair. That releases some of the lead and uranium as superheated gas. The gas then flows rapidly into a mass spectrometer for analysis.
3.787.
This sample is nearly 3.8 billion years old.
That's great. That's an old age. That's really exciting. That's very, very good. Yeah. That's the sad thing. You find a really nice zircon, then you immediately destroy it and drill a big hole in it. Yeah.
This rock is among the oldest ever found on planet Earth.
When you hold this rock in your hand, first of all, imagine that it has experienced about 1/3 of all time that ever existed. But also it carries a memory of the conditions in the ocean 3.8 billion years ago. So by studying these fine layers we have here, we can say, okay, what fell into the ocean? Were there any activities in the ocean? Were there life?
To find out, Dr. Rosing slices a sample so thin it allows him to look right through the rock's layers under the microscope. The geologist finds something astonishing. Tiny black grains.
What we can see here at very high magnification is some fine layers in the rock, and we can see tiny little particles of something black. And by closer inspection, it turns out that that black material is carbon.
And there's a lot of it, which indicates the presence of billions of tiny cells, the basic form of all life. Once, these tiny single-cell organisms drifting in the water were alive, taking in nutrients, reproducing, and then dying, dropping slowly to the ocean floor and decomposing into their final form, carbon.
That was really exciting because you don't normally find pure carbon in sediments unless it is derived from living organisms. So this was the first hint that there were life at that time, that we agree that these are signs of life.
It's the earliest known record of life on Earth, setting back the previous fossil record by hundreds of millions of years.
From just the fact that this rock is so rich in carbon that it's completely black, it tells us that the life was efficient, it was good at producing organic matter. And the only way you can basically do that in the open oceans would be if you live up in the upper few meters of the ocean and you use solar light for energy by some mechanism of photosynthesis.
And photosynthesis, a process that transforms sunlight into food, indicates advanced life. So scientists believe the first life probably goes back even further, to nearly 4.4 billion years ago. After a rogue rock the size of Mars hit early Earth about 4.5 billion years ago, It expelled molten rock into Earth's orbit. Then, in just 1 month, that orbiting molten rock stuck together, forming our moon. Not long after, meteorites bombarded planet Earth. They carried hydrous minerals, compounds that release water upon impact, and formed early Earth's oceans, providing the earliest opportunity for life.
The meteorites have the same composition of water as the oceans on Earth. Oceans were established 4.4 billion years ago, and the water that is now in the oceans has been here since that time, basically.
Along with hydrous minerals, it's conceivable that life, or its building blocks, also could have hitched a ride to Earth on a meteorite. It may have happened as recently as 1969, near the town of Murchison in the Australian outback, where strange-smelling meteorites, older than Earth itself, showered down across 13 square kilometres.
They are the fundamental building blocks of the Earth and of the solar system as a whole. The work that we do on them today won't be the final answer. There's a lot more work to be done in the future as techniques improve and new things arise.
These meteorites didn't hold life, but their odour came from something common to Earth: organic material. Under greater magnification, scientists discovered